Hey everybody, this is Mr. Beckstrom, and today we're going to be taking a look at a problem from section 4.5. This is number 26, and this was requested to go over, so let's talk about it. It says a man wishes to get from an initial point on the shore of a circular pond, so let's go ahead and call that initial point, point P. So he starts over here, and he wants to go on the shore of the circular pond with a radius of 1 mile to a point directly on the opposite side of that shore. So directly on the opposite side, let's call this D. That's his destination there. All right, so that's where he wants to get to. And it says that he wants to swim for some portion of it. So he wants to swim directly from this point to some portion. And then he wants to, I'll do that one in blue here, and then he wants to walk around the outside of the pond until he gets to that place directly on the opposite side. All right, so the first thing it says is if he swims at 2 miles per hour and walks at 4 miles per hour, what are the maximum and minimum times for the trip? All right, so let's talk a little bit about this. So they're giving us the rate of speed here, swimming at 2 miles per hour and walking at 4 miles per hour. So the rate of speed or rate is going to be equal to the miles, which is the distance, all over the hour, which is the time. So if we do a little cross multiplying and dividing, put like this, over 1, cross multiply and divide, we can also get that the time is going to be equal to the distance over the rate, right? Just cross multiply this and then divide both sides by rate, and you'll get the time is equal to the distance over the rate. Why did we just do that? That's probably what you're asking yourself right now. Because we want to optimize this in terms of the fastest time and the slowest time for the trip. So that's what's going to be in our objective function, is the time it takes for him to swim across the pond to one point. Let's call this point, we'll call it A. And then walk around the pond for the other part of this. All right, so we're going to have something that looks like this. We're going to have the objective function. Let's call the objective function capital D for the, we'll call it T for time. Call it capital T. So this is the time that he goes around, and that's going to be equal to the time it takes, we'll call that for swimming, little s, plus the time that it takes for him to do the walking. So we'll call that W. All right. So we're going to have to figure out what is this distance, and well, we already know the rate. The rate is given to us, so we can set that up. But we need to know the distance. So the distance, I found two formulas for the distance of the length of the chord. And a chord is from one point of a circle to another point of the circle. And the one that I'm going to use is, and we'll call it the C. The chord length is equal to, and like I said, the one I'm going to use here is 2 times the radius times the sine of theta, which is the central angle, divided by 2. Now there's another one that is 2 times the square root of the radius squared minus the diameter squared. And I'll show you a little bit in a second why I'm using this one. And then for the length of this part here, the arc length, well, the arc length, which they call S, is just equal to R times our theta. R times our theta. So notice that we know the radius of the circle. So this one right here is just going to become 2 sine of theta over 2, which is great because now that is strictly in terms of theta. And this one also, we know the radius is equal to 1 mile. So this is also equal to just theta here, right? So let's take a look how we can set this up. If we locate the middle of the circle right here, and we draw a line from that point to the middle of the circle, and to that point right there, we have some length here, and we can call that anything we want, but we're going to call that theta, right? And then we're also going to have this theta here as well, but it doesn't necessarily going to be the same size or same length as this one unless it comes down at a perpendicular angle. So this one, we know that the entire circumference is 2 pi, because it's 2 times pi times r, where radius is equal to 1. So half of a circle is pi. So if this angle here is theta, we can call this one here pi minus theta, right? So if this one here was 3 pi over 4, then this one would be pi over 4. If this one here was pi over 2, then this one here would be pi over 2. If this was pi over 4, then this would be 3 pi over 4. So we can set it up like that. Now everything's in terms of the same variable theta, and if we had used the other one with the r and the d, we would have had a harder time getting the arc length from the radius and the diameter. If you want to try that, you can, but that's totally up to you. But now I can set this objective function as t is equal to, remember, the time is the distance over the rate. So this first one here is going to be the chord length, so that's going to be 2 times the sine, and I'm going to call this, instead of pi theta over 2, I'm going to call it 1/2 theta. And then remember, this is the distance divided by the rate. So the rate of swimming is 2 miles per hour, so over 2. And then we're going to add the time that it takes to walk that arc length. So that is, once again, the distance over the rate. So the distance here is pi minus theta, all over 4. All right, so we're getting somewhere. So now, oops, let me go ahead and clean this up just a little bit here. So now, this is going to be equal to just the sine of 1/2 theta, or theta over 2, plus, and I'm going to call this pi over 4, minus, and that's theta over 4, or 1/4 theta. And I'm just doing that because it makes my derivatives a little bit easier. All right, and what we also need to do here is we also need to look at the endpoints. And that's going to be the time that it takes for him to swim the entire way, or, excuse me, walk around the entire way, and the time that it takes him to swim the entire way. All right, so let's go ahead and set that up. All right, so if he were to swim all the way across here, that's just going to be, remember, the time for completely just swimming. That's going to be equal to the distance across. Well, we know it's a radius of 1, so that would be a diameter of 2. All right, all divided by my rate, which is swimming is 2, I believe. Let me double check that. Swims at 2 miles per hour. So 2 divided by 2. So that is going to be equal to 1. All right, 2 right divided by a rate of 2 is equal to 1. And how about for if he were to walk around the whole thing? Well, that is going to be, let me see, if the total distance around is 2 pi, then half the distance around is pi. So that would be equal to pi divided by the rate of walking, which is 4. And that's going to be approximately, let's see here, pi over 4. So that would be second pi divided by 4. We get about 0.785. So 0.785. All right. And we already know that it is quicker for him to walk around than it is for him to swim across there. So now let's go ahead and we're going to check to see where any of the local mins and maxes are of this function. And we can do that by taking the derivative and setting that equal to 0. So the derivative of this function here is going to be equal to this is going to be equal to, remember, it's the derivative of the outside times the derivative of the inside. So it's going to be 1/2 cosine of 1/2 theta. This is the derivative of the outside, and the 1/2 is the derivative of 1/2 theta with respect to theta. This will zero out, and then we're going to get just a minus 1/4. Just a minus 1/4 when we take the derivative of 1/4 theta with respect to theta. All right, so let's go ahead and we're going to set that equal to 0. It's fun stuff, isn't it? So 1/2 cosine of 1/2 theta minus 1/4 is equal to 0. So 1/2 cosine of 1/2 theta is equal to 1/4. Multiply both sides by 2, and we're going to get the cosine of 1/2 theta is going to be equal to, multiply that by 2, you get 1/2. So here we're going to have 1/2 theta is equal to the inverse cosine of 1/2. And let me give myself a little bit more room here. That's taking the inverse cosine of both sides. Now, what is the inverse cosine of 1/2? Well, that means the cosine of what angle gives us a 1/2, and that's going to be pi over 3. So the 1/2 theta is equal to pi over 3, and multiply both sides by 2, and we're going to get theta is equal to 2 pi over 3. All right, so that means that we have a critical value here at 2 pi over 3. So let's check out what that is, and let's go ahead and use our calculator for this part. So remember, this is the function here that we're trying to minimize. So let me go ahead and put that in my calculator here. All right, so this is y equals, and make sure we are in radians, which we are. All right, and this is sine of x over 2 plus pi over 4 plus second pi divided by 4, and then minus, that would be x over 4. All right, enter. Just double check that. And let's go ahead and evaluate this. First of all, remember, I'm going to go to second window, make sure that's on ask, delete. Let's make sure these values are correct first. So this first one is if he swims the entire way. So he swims from here to here, which means our theta is going to be equal to pi, because it's going to be half of a circle. So let's see what we have when we put a pi in there. Sure enough, we get the 1 there. Now, if he walks the entire way, that means our theta is going to be equal to 0. Let's put a 0 in there. Sure enough, we got that 0.785. Now we're going to check that critical value of 2 pi over 3. So 2 pi divided by 3. And it looks like it's going to take us even longer to walk around the circle, or to do that than it took us to do the other two things. Let me make sure that that point was right. Yep. So the fastest way to do this for part A is if he walks the entire way around the pond. He walks the entire way around the pond. So I want you to go ahead and try B and C. Really all you're doing is just changing Well, for B, you're going to keep this at 2 here, but you're going to change this to 1.5. And then for C, you're going to keep this here at 2. And then it says, what is the minimum walking speed for which it is quickest to walk the entire distance? So see what you come up with that, and let me know in the forums. All right, thank you, everybody. All right, bye-bye.